Hello and welcome. We're at the Lorentz Center in Leiden today with Professor Grubisic-Cabo, or Antonija, Professor Ali, or Maz, and Dr. Kurdi, or Samer.
Nice to be here.
Yeah, and today we're going to be discussing two-dimensional magnetic materials. So I guess the first part of that is, what do we mean by magnetic material? Are we talking about something like a compass or a fridge magnet?
Well, sure. A fridge magnet is well known to everybody. It's made out of a ceramic material called bismuth ferrite. And it's actually a ferrimagnet, not a ferromagnet, if everybody knows what that means. But it basically means that not all the spins in the material, which are what's causing the magnetism, are aligned perfectly with each other. Some are aligned together after a little space. Some are not aligned with those original spins. And so there's not a overall sum of all of these moments in the same direction. Some are counter. And so it's a little weaker than it could be. And but it still makes a pretty decent magnet to hang up your kids' drawings on the fridge.
And what do you mean here by spins?
So I think if we can just backtrack a little bit. So I think we're all familiar with a magnet in terms when playing around as kids. There's a blue part, there's a red part. One's the North Pole and the South Pole. So we can have magnetic repulsion and attraction. When we bring these North Poles together, we see a repulsion. When we bring these North and South, they attract. And like Maz said, the underlying, to make it more complex, magnetic materials are made of, or materials in general are made of atoms. These atoms carry electrons, and these electrons are also carry a thing called spin, which are very tiny magnets. Now, some materials, or you may ask all materials, why are not all materials magnetic? Well, first of all, they all have electrons, so why can't they all be magnetic? Well, these spins, if you can imagine them as an arrow, in most materials, these arrows point in random directions, and therefore the net magnetization cancels out. Now, in a magnet, these spins are mostly pointing in one direction, resulting in what we call a net magnetization. And this is exactly why a fridge works. Or how a fridge magnet works. We can take this magnet, which has a net magnetization, we bring it very close to the metal, which is the fridge door, and then it magnetizes that metal, and then there's a net attraction. We can put our nice pictures up and things like this.
Okay, so we have a whole lot of compasses and they point in a specific direction. Little tiny compasses is what you're saying, each of these atoms.
Yes. So you can imagine all of these spins. It's like you can imagine atom like being your tiny compass, and needle just points up or towards north or down towards south. And I think we were actually asking about 2D magnets. So now we know a lot about magnetic materials, but what is a 2D magnet? And you can just imagine that everybody loves Post-it notes, right? Imagine that you have a Post-it block and it's actually magnetic. But then you start to take like just individual pieces of Post-its, and that would be your 2D magnet. So it would still have these little compass needles within that just tiny, tiny sheet. But you know that once you take this sheet, it's completely different from the block. Like you can stick it to places, you can bend it, you can twist it. So it's still a magnet, but it's very thin, and it kind of behaves completely different from your Post-it block.
So how thin are we talking compared to a Post-it note? Or say a human hair?
I think roughly like 10,000 times or so. And then we get to really an atomic piece of paper is how we can imagine this.
So we're talking about a single layer of atoms here.
Yes, which is astonishing that we can make a material which is atomically thick. It's really amazing to think about.
Or not just make, but peel apart something that is starting out like the block of Post-it notes and actually just peel off using Scotch tape. Shockingly, that's what won the Nobel Prize a while back by Nosolev and Gaim. And you can peel off with Scotch tape one atomic layer at a time. That's what was done with graphene, which is a single atomic sheet of carbon.
Okay, and they use the same method now for 2D magnetic materials.
Even more shockingly, maybe, it's actually one of the most popular methods in science to make anything 2D, including magnets.
Okay, so the entirety of two-dimensional scientific studies rests on Scotch tape.
Not all, but kinda, yes.
Almost all.
It's a powerful tool. Shockingly powerful tool.
Okay, so we've got a two-dimensional magnetic material, but why are they useful? Why are they interesting? Let's start with perhaps why are they useful?
Well, I think if we can just backtrack a little bit and just look at conventional devices. So I think magnets are very interesting because they can be used in various types of disciplines. So we use them, we've mentioned fridge magnets, we've mentioned compasses, but we rarely also use them in healthcare. I play a lot of sports, have many injuries. I go to the hospital and I get a very detailed magnetic image via magnetic resonance or MRI, where it's called. What's also important is that it's also used in technological-based devices, like computational-based devices, and even data storage. So you can imagine a hard drive which has a kind of a disk which rotates, made up of very tiny magnets. And there's a very sensitive magnetic sensor which is used to read out the magnetic state of these individual tiny magnets to lead to a kind of information about what we're storing using our computers. Now, we also have a cell phone, right? We see that over the years, this cell phone has actually reduced in size and somehow also increased again. But relatively, we see the trend that we're decreasing size of technology. We're making them more efficient. And now this tiny device is actually much more energy efficient, and we can do much more powerful things with it compared to these big computers which were developed back in the 1960s. Now, of course, I think one interesting aspect is now by reducing from a three-dimensional object, which has a width, a length, and a depth, I should say, we remove the kind of the height or the depth, and then we're able to miniaturize these materials to 2 dimensions, which would lead to even smaller devices. I think that's one interesting aspect of it.
Okay, so you can make things much smaller, so we can have more powerful computers, more powerful phones. Right.
And maybe we can even make them in completely different shapes, because you know how I said you take one sheet of Post-it, you can bend it. If you make things 2-dimensional, you can even think of, foldable, bendable. We already have foldable phones, but you could just roll it, put it in a pocket, and it should still work in theory.
So I could have an even larger phone.
Large screen with very bendable tiny phone.
Right. From a also very fundamental aspect, quantum mechanics manifests at the very small scale. Mm-hmm. So a lot of classical computing and classical technologies, or semi-classical if you want to call it that, have been big and took advantage of what we call classical properties and classical understanding of how electrons move in space and how many electrons together make, classical magnets. But when you go down to this single atom thick or couple atom thick level, they're not as easily described using the methodologies of the early, 60s and 50s and whatnot. And nowadays, we even think about how they work differently in understanding them more as waves rather than particles. For example, understanding that the energy levels that they jump into or out of the electrons, are quantized and not continuous anymore. And so all of this manifests different in more interesting, or let's say new phenomena compared to what we used to explore and what we used to know. So there's a lot of opportunity to understand sort of the nano universe. We now have the James Webb Telescope and everybody's looking out at the big, but there's a whole universe down there that we are just now getting to really explore.
So these 2-dimensional magnetic materials can have some special properties that you might otherwise not get.
Yes, very much so.
Right. And is that it for they just happen to be interesting on their own?
Well, actually some are. Yeah.
I was going to say yes to one additional point is that there's a whole zoo of 2D materials, which are even non-magnetic, and we can kind of stack these on top of each other, and we can then utilize their kind of unified properties by putting them on top of each other to realize even novel physics, which is there's so many different parameters to explore, so many materials to stack up and even twist their orientation relative to each other. And this really brings into a new field of physics, which many of us in condensed matter physics are really eager to explore.
So you can imagine it sort of as, well, we often say chemistry is like cooking, but in this case, it's more like you're assembling your own sandwich. So you have your individual ingredients, you have some nice bread, you have bacon, lettuce, tomato, everything great on its own. But then when you put it together, you get something completely different. Some would say much nicer than individual ingredients. So we call this emergent property, something that is just like shows up as a surprising effect of combining things that they're very different. You put them together, it's something amazing. And you can just then swap your lettuce with something else. Well, or if you remove lettuce, it's a completely different sandwich. And it's kind of similar with all of these 2D materials. You swap one, you take another, completely different thing.
Right. So essentially, I have a bacon, lettuce, and tomato sandwich, and the whole is greater than the sum of the parts here.
The whole is greater than the sum of the parts. And that is what is super cool about these materials.
Well, sounds delicious. So I guess the question then is, why exactly aren't we using these all the time? You know, why do we not have them in our phones? Why are we at a scientific conference rather than, you know, buying them in shops?
Ooh, that's a very good question.
So let's keep in mind, right, the first 2D material that won the prize was only isolated about 20 years ago for the first time. So it's a relatively young field to be able to, again, use Scotch tape, or now we have some fancier tools than Scotch tape, but Scotch tape does still work. But it's a relatively new field, and it's relatively new for us to be able to explore down there. Since then, material scientists have been making lots of different types of materials, and we're finding more and more interesting 2D ones. And then we're trying to go down to the 2D limit of those materials. But it's a slow process where you really want to know what you're doing every step of the way. It's important to characterize really well, to examine really well the material in its bulk form. And then as you go down thin, so you really understand what's coming about, like the analogy we gave about the sandwich, what's coming about that's new and arising really from the reduction in dimensionality, the 2D nature rather than the 3D.
Okay, so you need to look at, firstly, this stack of Post-it notes, and then look at the individual Post-it notes before you put them all together into some new stack of Post-it notes.
I mean, to continue the cooking analogy, if you had never tasted any ingredients and you tried to cook something with them, you'd have no idea what you're going to get out, right?
You wouldn't know to make a bacon, lettuce, and tomato sandwich.
Probably not.
And then I think the second point is to add to that is that using Scotch tape, we can only get small size samples. There's a whole need to push for kind of a manufacturing method and a way to produce these on a very large scale to make them compatible with current manufacturing of commercial devices.
And just to, avoid confusion, we want materials small, but more like thin in a 2D scale. We kind of want them really, really large, like in plane. So basically what we want to have is like, a giant sheet of just atomically thin material. It's very thin. It's going to get miniaturized, but in plane it's huge, and we can make a lot of, let's say, cell phones or different kinds of memories like really quickly, and not just slowly peeling things off like for days at a time to get our, little chip.
So a very large piece of paper.
Very large.
So you want a very
paper.
large piece of paper, not to have individuals going through and tearing off little bits at a time.
Exactly.
Because that would be incredibly inefficient.
Oh, yeah.
Right.
And do these devices, as it currently stands, do they work? If I were to grab a piece of two-dimensional magnetic material now, would it work like a fridge magnet?
If you're very cool.
I am very, very cool.
It would hold up. For example, if you took it and you tried to attach something to the fridge, a mono layer of magnet today would probably hold up another mono layer of non-magnet of your piece of paper if it was also atomically thin. Mm-hmm. Like the strength of the magnet is partially related to how much magnet there is. And so these are very thin magnets, which is why when we're trying to use them in technologies, we're also trying to get down and touch them very close and in a very precise way, not on a very massive way.
And one thing we actually didn't mention so far is that these magnets, when you take your compass, we actually want all of these tiny compasses to point in the same direction. And, well, they tend to do it at certain temperatures. And when you take your nice fridge magnet, which Maz told us it's ferry, not ferro, so almost all compasses are looking the same way, that we say that it's in magnetically ordered state. it works at room temperature like a charm. But so far, a lot of 2D magnets we have work at like very, very low temperatures. So maybe not you, but your room would have to be crazy cool or cold to make these things stick.
How cold are we talking about?
Outer space.
Right.
Yeah.
So a few degrees Kelvin, so minus 270 or so degrees Celsius. It's a bit colder than a fridge.
There's literally no place on the planet naturally cold enough.
But is there the potential to increase this temperature?
Yes, so there's currently a lot of research directed towards that route. So a lot of theorists doing some very complicated calculations to see how we can kind of predict and manipulate the atomic structure to be able to get a higher temperature of operation of these magnets.
Yeah, there are groups literally around the world working on this, including right here in Leiden and elsewhere in the Netherlands, who are trying to raise we call it TC, the critical temperature. And for some materials, it's up to about 70 Kelvin from, 2. So that's a good progress, I'd say. That's pretty fast.
And how long has that taken to go from 2 Kelvin to
7 years maybe.
Right. So it's fairly fast progress.
Yeah, it really is.
There is hope.
There is hope for very, very thin magnets that work at temperatures that are reasonable.
Yes.
Yeah.
And what about in terms of increasing the size? Is the progress on that similar, or?
I would say not. I think as a community, we're really focused on just understanding the fundamental properties currently, because there's a lot of new materials which we're discovering every day. And like we said, we can make many different types of sandwiches, and we really want to eat these sandwiches all before we think about before we think about how to scale them up. But I think eventually there will be a push for this, and we've already discussed this in this meeting.
Yeah, and you also have to think about, Samir just said there's a lot of these materials, but you don't necessarily want to grow a huge bad 2D magnet. So we really want to understand like which one is the best, which one makes, let's say, the best sandwich, and then we look into how to make them bigger and with a really, really high quality, so you can also use them in devices.
So right now I'd say you're taste testing the two-dimensional magnets.
We're taste testing.
Right. Give us 5-7 years and we'll be ready to cook.
Yeah.
Maybe 10 years.
Okay, I think we're out of time now. But thank you all for coming along and explaining the wonders of 2D magnetic materials.
Thanks for having us.
Absolutely. It's been a pleasure.